For those students that couldn't make it, welcome. We'll start over again. So thanks for joining me today on Friday. The point is really to, I don't want to rush this fundamental material. It's very important that we're just going to build off of. Of course, we don't know how we calculate electrons. It's going to be very hard to calculate the current in a device if we can't get how many electrons there are or how many free charge. And what I have here in my hand is I have a crystal model for a diamond lattice, which is, it's also called a zinc blende lattice. And it's called a diamond lattice because this is the crystal structure of diamond. It's also the crystal structure of silicon. And if you look on the periodic table, carbon's up here, you go one row down, you have diamond, you go one row down again, you have germanium. And they all form the same, at least they have stable compounds that all form the same crystal structure called the diamond lattice. Okay? Also called zinc blende. Okay? So this is also the same structure as gallium arsenide, except every other atom, one would be gallium and the other one would be arsenic. It's also the same structure as indium gallium arsenide, but you're going to have an alloy of the indium and gallium. Okay. So I'll pass that around. What I'll ask you to look at is, yes, you know, it's repeating in all directions, but it definitely is a crystal. There's definitely certain planes that you can see through in a different way. And so while we won't get too much into, you know, how things vary anisotropically, meaning how things are not uniform, and isotropic meaning uniform in all directions, iso meaning equal, and isotropic meaning not equal in all directions. We're not going to dive into all those details, but we can change some of these masses and things like that to take into account that maybe electrons flow faster along one direction of the crystal than maybe a different one. Okay? And so I'll pass that around. I also wanted to show you, maybe some of you have heard of the 2D semiconductors. That's my research specialty here at Columbia. This isn't a 2D semiconductor lattice. This is the lattice for graphene. And so this is a 2D material. And so why do we think it's called a 2D material? How is it bonded? How is the bonding different?
Interlayer is van der Waals interaction.
Yeah. And so what's you know, the interlayers aren't bonded together. They're we call it a van der Waals bond, which is just kind of like a proximity bond. It's not actually really sharing electrons. It's just when two materials get close to each other, they create a slight dipole, and so there's some bonding due to that dipole, but it's not like sharing an electron, right? There's ionic bonding, really strong bonding. Covalent bonding, less strong. Van der Waals bonding, even weaker. Okay, it's just proximity bonding. And so these planes are bonded. These semiconductors are bonded in plane. That's where most of the bonding happens, and there's no strong out of bonding. And so these exist as sheets, and that's why maybe for those of you that are old-fashioned and using a pencil to write with, instead of a $200 Apple pen, go technology. A pencil, why can you write with a pencil? Well, what is pencil? What is the pencil lead made out of?
Graphite.
Made out of graphite. That's multiple sheets of this. That's all it is. Graphite is multiple sheets of this graphene lattice. A single sheet is called graphene. And these sheets shed off. They're not strongly bonded, so you write with your pencil and you leave sheets behind on your paper. And the thing that's unique about graphene is we've been kind of using it the whole time, which wasn't known, is that a single layer of graphite called graphene was stable. That's what was not known. It was known that graphite was a layered material. It was known that you could layer it off and break layers. It wasn't known that a single layer was stable. Some initial theory had said a single layer would not be stable, so nobody really looked for it. But then in 2004, anybody know the story of graphene? How it was first kind of made in a reliable way?
Use a tape to
Yeah, yeah.
set it down.
So they took Scotch tape, you kind of put the crystal in between it and you pull it back a couple of times, and every time you do it, you kind of separate the layers more and more. And then probabilistically, if you look across that tape, sometimes there's little flakes that are just a single layer. Not every flake is a single layer. A lot of them are really thick, but if you look over a large enough area, probabilistically, sometimes you'll have a single layer. And so what's incredible about it is you can actually see it optically. There's a little contrast with that layer. And so your light setting has to be correct and everything like that, but you can actually see a single layer absorbs about 2 to 3% of the light. So you can actually see that contrast with your eyes. So it looks like you see a little shadow in that region. Not a super dark shadow, but I just wanted to give you an introduction to kind of, there's not just silicon out there, even though that's what we'll be focusing on. Are there any other questions before I jump into the lecture?
So is silicon isotropic or anisotropic?
That's a good question. The question is silicon isotropic or anisotropic? What do you think? I mean,
I thought it's isotropic, but now I kind of think it's anisotropic because it's different looking at different way.
So what do we think? In the broadest definition of isotropic, it means iso meaning equal in all directions. Does anybody have any other thoughts? Do you think it's isotropic or anisotropic? Any strong opinions in the class? I'll let you think about it. Or I'll have an awkward pause, let you guys think about it. And then I'll force you to make a decision. Isotropic, meaning equal in every direction. So that is. Okay, left hand for isotropic, right hand for anisotropic. Okay, left hand for isotropic. Right hand for anisotropic. Yeah, it's anisotropic.
Okay.
So if you do a 90-degree rotation, let's see if I can do this. Okay, you see that? Okay. It's definitely the same about a 180-degree rotation, but if I do this 90 degrees, 90 more degrees, 90 more degrees, those are equal. But if I'm not at 90 degrees, and I go a little bit, that's not isotropic anymore. And there's a different effective mass and different transport in those directions. Typically, because silicon is anisotropic, so there's different degrees of anisotropy, meaning that you can have a material that's wildly anisotropic, right? And so it really varies the pattern for graphene. Somebody stole my graphene. But the graphene is, that has a periodicity of 30 degrees, right? Or 60 degrees. It repeats. But yeah, silicon is not. When we make our devices on a wafer, we orient our devices intentionally along different crystalline directions because they have different performance along different directions. So typically, the channel of most devices is aligned along the 110 crystal direction. That numbering corresponds to a specific direction along the crystal. That's a great question. Okay, we're learning a lot. Good. Any other questions? The last thing I'll say is the graphene layers, at least from our macroscopic point of view, they kind of hover next to each other because there are electrons out of plane. It's just those electrons kind of, the atoms don't want to be infinitely close to each other. So there is some distance between them. It's about 0.3 nanometers between each layer for graphene. There's also 2D materials that have a similar structure, meaning they're bonded in plane, but it's 3 planes. You know, you have so the semiconductors I work with, tungsten diselenide, you have a middle plane of tungsten and it's bonded out of plane to selenide, and that's it. So it forms one layer, and then you have another layer of that on top. So it's not just a perfectly atomic sheet, but it's a three atoms. But it has slightly different bonding. But if you look down from the top, it's still hexagonal in symmetry. Okay? So in last class, we were talking about this density of states formula, and I would like to tell you all everything, but I want to get to the MOSFET, I want to get to the short channel, so I just can't derive everything for you all. Otherwise, we're just going to be overloaded, and we're just going to start talking about, well, why do atoms exist? Why does this? And so what I can tell you is, okay, these are the density of states. It shouldn't surprise you that the density of states is not perfectly flat if you think about how we got these bands in the first place. All the states, you know, as we put more and more atoms together that bond, the states shouldn't necessarily be equally distributed in energy. There's nothing to say that's the case. And of course, what we saw experimentally is it rises, and then there's some kind of interesting peaks here, and then it kind of has some weird behavior. But we really only care about these, the density of states right near the band edge. Why is that? Well, because we don't have all the pieces working together, but we can kind of see these things separately. We know there's going to be some Fermi level that represents some equilibrium condition. And we know with the Fermi level, the Fermi-Dirac statistics, the occupation that these states have with energy is dying exponentially. And what's the constant with that? So let me say that a little more clearly. With the f of e function, that's just the probability of a state being occupied. It's going as right in the Maxwell-Boltzmann limit. MB means Maxwell-Boltzmann. I've simplified, and this is for electrons. Remember, there's a different approximation for holes. F of e is approximately exponential of negative e minus EF over KT. Okay? So as this is how we typically draw the picture. So at a given E, this is E minus EF, that's what that distance is. As this E minus EF gets bigger, my exponential decay, there's more exponential decay, or my probability is exponentially decreasing. So every KT, if I go up, if I increase E by KT, I've decayed by my exponential, my argument becomes one margin. So if this was, so it goes from e to the minus n to e to the minus n plus 1. So it decays by a factor of e. For every KT, I go in energy, my probability decays by a factor of e. Is KT big or small? It's small. It's 26 millielectron volts. And it's kind of interesting that we have an intuition that that's small. That's partly because of the units we're using. They put it in a physical framework that, okay, we know millivolts are small. We just have a feeling for that. But yeah, it is small. And so I just go up 26 millivolts, and I decay by E. And what you can also see is that if I don't want to see when it decays by E, I'm going to leave this math for you. It's going to come up again and again and again in the course. But my question is, how much do I increase E to reduce f of e by 10x. Okay? If I ask that question, so it says how much, I'm at some probability, how much higher in energy do I have to go for that probability to decrease by a factor of 10? And if you write this now, instead of, this is written as an exponential, you can write it as a power of 10. You'll find that the number you get is kT natural log of 10, which equals 60 millivolts. Okay? This number is not going away. Notice, it's directly proportional to kT. And okay, I'm just converting this to decade because a decade means something. When does something drop by a factor of 10? Okay, that's a little more intuitive to when it drops by a factor of e. Okay? But you can see they both depend on the same thing. There's just a constant. 60 millivolts. So what that means is every 60 millivolts I go higher in E, my probability drops by how much? By 10. Okay? And so the shorthand that we write this is we say that there's this 60 millivolt per decade, sometimes just written as DEC, but per decade rule. I'm just translating what this means. It just means what I said here. For every 60 millivolts you go higher, your probability is decreasing by a factor of 10. But it's not, it's more general than that, right? For every 60 millivolts I go lower, my probability increases by a factor of 10. So if I'm at some point here, and this is 60 millivolts above the band edge, and this is all assuming my Maxwell-Boltzmann approximation is valid. Somebody want to remind me when this approximation is valid? Yeah, so this is valid when E minus EF is greater than 3 kT. The most fundamental form of this is the Fermi-Dirac version. This is the true version. Okay, this is where it's coming from. The Maxwell-Boltzmann is just when this term is much greater than 1, and then we approximate it as that. That's it. So the 3 kT, when I'm 3 kT, this term is about equal, when I'm at the barrier, at the smallest, when is this approximation worse? When E minus EF is the smallest. When is E minus EF the smallest? At 3 kT. If I plug in 3 kT back in here, I get an exponential of 3, which is about 10. So, 1 plus 10, that's almost equal to 10. I have pretty low error there. Okay? So I'm spending so much time on this because this is the underlying physics for everything we're going to be doing. Okay? And this is what makes semiconductors so special. I have a little change. Okay? We don't know how to do it yet, but I'm going to give you something to think about. If I have something that can move the Fermi level with respect to the bands by 60 millivolts, what would happen to the charge in the conduction band? So if I move my Fermi level, I had some case, and somehow I had some tool to move my Fermi level down. We don't know how to do that yet. We're going to see some way to do that. But if I could move this down by 60 millivolts, what would be your guess of what would happen to the number of electrons in the conduction? It would reduce by 10x. What if I, instead of moving it down by 60 millivolts, I moved it down by 120 millivolts? 100x. Now 180 millivolts, 1000x, okay? So if I just move this, maybe I'm going to use some electric fields or something like this to move it. And if I can move it by 180 millivolts, I've changed my electron concentration by 1000x. That's the leverage here. That's an exponential change. And that seems like it's something that's very powerful. And it makes a really good switch, right? I just put a little bit of an input, and it gives me a big change in the output. And I can keep doing that, and that's what's special. I can do this over many, many decades. So I can vastly change my carrier concentration in my semiconductor. And in case it wasn't quite clear, why does my total electron concentration in the conduction band change by 10x when I move this down by 60 millivolts? Well, you can look at each state individually. The population here, this increased, the distance increased by 60 millivolts. So the population right here, at this energy, the probability is 10 times less. Well, what about the probability here? Well, I increased E minus EF by 60 millivolts. So the probability here decreased by 10x. And here it decreased by 10x, and here it decreased. So everywhere here, it decreased the probability of all these states by 10x. I have the same number of states as before. I decreased all their probabilities by 10x. So I have 10x fewer carriers in the conduction band. When I integrate over all energies, I have 10x fewer carriers. And so it's not that I'm just changing the ones here. And that has to do with this exponential tail. I'm kind of changing the probabilities of all. Okay, kind of cool. Is that making sense? Okay, so now you've got an intuition. Now we're going to do the math to make all these calculations happen. Okay, but that's the math. The math is how you get the number. This is how you get intuition. Okay? Before I get into the math, we always have to understand our approximation. Does this approximation work if I have a situation like this? And EF is in the band. No, it doesn't, because I've broken this approximation, and I no longer have this pure exponential dependence. So if I move this down by 60 millivolts, I don't exponentially change the state there. Maybe the ones really, really high up I do, but these aren't changing exponentially because I'm shifting it like this. And so these states would have decayed exponentially, but this one, the ones near there, okay, you can think about that. Okay, so let's do this. Okay, so these are the equations. And this is well understood how we get these equations. I'm not going to derive it, but these are the equations that tell us how many states there are per volume, per energy, density of states in our semiconductor in the conduction band and valence band. And yes, there's a difference in the minus sign, but if I really, really encourage you to draw the picture. I draw the pictures. When I'm trying to solve these problems, I have to draw a picture because here, if I'm trying to integrate the states in the valence band, it gets a little confusing to me because I'm integrating negatively. I want to make sure, but then this is that way. And so I have to draw a picture to help me make sure I'm getting all my signs right.
This should be E minus EV or EV minus E, because EV is larger than E.
So this is correct here, right? Because this is an EF, this is just E. So it's saying the density of states at some E for the valence band.
Okay.
And if I'm above EV, this isn't valid. So it's growing this way.
Okay.
So it's growing this way, but I'm integrating this way, And so I can flip it around and integrate it this way, but it's easy to confuse yourself. So it's going like the square root of this, you know, the energy above the band. And there's some prefactor that has to do with this effective mass, okay? The effective mass is telling us how many states there are there. Okay, and there's two different types of effective mass. There's a density of states effective mass, and there's going to be a conductivity effective mass that you see later. Okay, and this effective mass is, I mean, if you like, it's telling you how many states. It's you can look at it in reverse. It's some parameter. You know, this is how many states you have with energy, and you can back calculate. Well, what's that effective mass that gives you that? Of course, you can do it in the forward direction as well, but it's telling us something about how many states there are with energy. Okay. So look at how many terms we are, and we're just done with, yeah.
So when we calculate the effective mass from the energy band diagram,
Yeah.
what effective mass does it refer to?
Okay. Okay. So let's do this. Have I shown y'all the EK picture? I've shown you the EK plot. Did I show you energy versus momentum in this class? Yes or no? Okay. All these plots are energy versus position. Okay, that's what I mean here. So this is like position in the crystal. Everything's uniform in our crystals so far, so everything's flat. But I could also write energy as a function of momentum. Okay? And this is commonly called the K vector. Why is this? Well, I can represent electrons in my crystal like this. Something like this. This is just a wave. This is a traveling wave. Okay? My electrons, duality of matter, particles, everything has a particle nature and a wave nature, matter included. So I'm not going to do justice to this. I'm just trying to provide a little background so it's not just, this is all magic. I can represent my electrons as a wave in the traditional sense. This K is equal to 2 pi over the lambda, where lambda is the wavelength of that electron. As it turns out, h bar k, h bar being Planck's constant, is related to a momentum. It's the crystal momentum of that electron. Okay? So I can plot energy versus momentum of these electrons. And I get a picture like this. EC, EV. Okay, these are the band edges. And so I'm not telling you how I'm solving this. I'm just telling you this is what you get when you solve the crystal. Okay? When we solve the band structure, we're really solving it for each momentum state. Well, these energies are actually at different momentum states. Okay, not the net number of states going left and right is the same, but the band, all those states are not stationary states. They're actually traveling states, okay? And so here I'm just drawing the bands as a function of position. So we don't have that information in this picture. I can't draw everything all together. But I can also draw the bands as a function of momentum. And they look like this. And so there's actually states, you know, at all these different momenta. Okay? And these are the states that the electrons are allowed to be in. These are states referring to holes. Okay. Now, what's the relationship between energy and momentum?
P squared over 2m.
E is equal to what? Maybe I'll write kinetic energy is equal to what?
P squared over 2m.
Oh, you guys are fancy. Okay. So typically people tell me this, 1/2 mv squared. That's something a lot of people are familiar about, but it is exactly the same as p squared over 2m. When I solve my bands, when I solve the allowed crystal modes, electron wave modes in my crystal, and I find out what energy they're at, I get this. This is an output of me solving this crystal. I put this crystal in, I solve the Schrodinger equation for this crystal. I get, these are the energies that are allowed. These are my energy states. But each energy state, the reason they're at different energies is they also correspond to different momenta. Okay, so I get this. This is my output of my solver. Now, this tells me that E should go, what should be the relationship between E and momentum? Squared. It should be a parabola. And indeed, it is a parabola. It's a parabola where the shape of that parabola is related to something that we classically would call the mass. This is true for any particle. Plot the kinetic energy as a function of momentum for anything, for you. And it should look like a parabola. If your momentum is going this way, your momentum is going that way. If your momentum is twice as much, you have 4 times the kinetic energy. Okay, that's why high-speed crashes, 100 km/h crash is not equal to just twice as bad as a 50 km/h crash. It's equal to 4 times. You have 4 times as much kinetic energy. That's why the speed limits are, okay? Kind of think about that. It's not just twice as dangerous. But as it turns out, this mass isn't the mass of a free electron. That's not, we put the crystal in, it's not a free electron. It's not the free electron mass. It's this electron propagating through a crystal. And this curvature, this is just what we solve when we put in the atoms and we solve what the allowed electron waves are in that crystal. Okay, this is the solid state physics part that I'm not deriving. You know, there's a 1 semester class to derive all this. Okay, and then at the end of the class, you would have derived, this is like the culmination of that class that I'm doing in like 5 minutes. Okay, but I get this curve, and it happens to be parabolic. But the curvature can be like this. For different semiconductors, it might be like this. For another semiconductor, it might be like this. Okay? And I can just say, oh, well, this looks like, this semiconductor looks like it has, for a smaller curvature, is it a larger or smaller effective mass?
Small.
Yeah, the smaller m is, the more, the steeper the curve is. The larger m is, the flatter, and my effective mass can be larger than the free electron mass, and it can be smaller. It can be much smaller. It can be like 1/100th of the free electron mass. It can be twice the free electron mass. And guess what? It depends on the crystal direction that I'm traveling through. Okay? So this is the effective mass. Okay? Now, the reason why it's coming into the density of states, it's not a mystery anymore. Okay? Well, remember this is 3D. You're only looking at it in 1D. But you look at how many states there are in energy, and you can see if the mass is smaller, there's going to be a lot fewer states at a given energy. Because the last thing I told you is my K's, my spacing of K is set by my crystal size. Those are like kind of my waves that fit in my crystal. They're periodic with the crystal size. Okay? So these are kind of set. So as I change my effective mass, I have a different number of states per unit energy. Larger effective mass, more states. When I do this in 3 dimensions, I get this 3/2 power of mass. If I had a 2D crystal, is just going to go as mass to the first power, and there's not going to be an energy term. It's just going to be constant. So this density of states depends on the dimensionality of the crystal and the effective mass, right? I'm counting how many states there are. Now in a 2D crystal, this is also going to have a different unit, right? It's not number of states per volume per electron volt, it's number of states per area per electron volt. So we're going to use them similarly, but they're not, it's not like, they're different units, right? It's like comparing a sheet density to a volume density, okay? So that's the background there. Now this mass, this density of states mass, is some average in all directions, okay? Because I just care how many states there are at an energy. I don't care whether it's going left, right, up or down, front or back, okay? So that's kind of like this, I have to do my averaging in a way that makes sense, but I can do that, okay? And that mass is taken into account that. Remember, all my masses are not necessarily the same in all my different directions. Now, I'm gonna have a conductivity mass. My conductivity mass, I really just care, if I apply a field this way, how easily can my electrons move that way? And it's gonna turn out to only depend on the mass in that direction. So if everything was isotropic, these masses would all be the same, but it's not. Okay? So maybe that's less of a mystery now. Well, it opens up a mystery to be better understood. Okay, that's making sense? We're feeling good? Uncovering the mysteries of the universe, right? All in 633. Okay, so now let's actually calculate these things. I know you guys, you're like, give me some equations. I'm really good with the calculator. Let me do this, okay? So, how many electrons in holes are there at, what's TE? Thermal equilibrium. Remember, thermal equilibrium means my energy, my average energy is the same everywhere, because if it wasn't, then I'm not in thermal equilibrium, because then my energy needs to spread out in a given semiconductor. And so the answer is we need a model, exploiting this energy view of the semiconductors, okay? And I already gave you the introduction to it. I already gave you the equation. My goal here is just to make sure you understand it. Okay, so my electron concentration in thermal equilibrium, of course, depends on my location of EF. Why is that? Well, EF is telling me my probability of occupying the states. If I move EF that way, then I'm going to have fewer states occupied here. If I move my EF this way, then I'm going to have more states. Can I move my EF into the band? Yes, but then I have to use a more difficult form of F of E. I have to use the Fermi-Dirac form with that extra pesky 1 in the denominator. Okay, but that's it. It's just much nicer to deal with the exponential. You can always deal with Fermi-Dirac, but you're not going to be able to get analytical expressions, because the integrals you're going to do are not going to come out to something simple. It's just going to be an integral that you say, well, that's my answer. It's this integral. I got to solve it. And my question is, well, if I change my temperature by 5 degrees, by a factor of 2, tell me what happens to my carrier density. And you're going to say, I need to calculate the integral. I'm going to say, well, does it double? And you're going to say, I need to calculate the integral. And so it's not very helpful from an understanding point of view. Sure, you can do it numerically. That's easy. You just put in another function there and you do your integral. But it's very hard to get these analytical equations that you need, because your function at a company, your function at a university is not going to be to calculate these things. It's going to be to give meaning to these things. Somebody can already calculate all this stuff much faster than you can. Okay? It's for you to understand it so you can extrapolate it and apply it in different ways. Okay? So, if I multiply these two functions together, probability, this is unitless, just probability, times my density of states, I'm going to get a distribution of electrons. It's going to look a little funny, but okay, it is what it is. And this is my number of electrons in equilibrium, N naught, per volume, as a function of energy. That's just from multiplying these two together. Okay? Now, N naught of E, there's just a lot of terms in this class. N naught of E is not the same as N naught. They're in different units. N naught of E is per energy. It's the per volume per energy. And if we integrated N naught of E, we would get the total number of electrons and the conduction band per volume. We're almost always in volume. And I've already given you a really, really fundamental thing. If I screw my EF back by 60 millivolts and I'm in the Maxwell-Boltzmann limit, then I'm going to decrease all these states uniformly, but it's equivalent of multiplying this whole thing, dividing it by a factor of 10. All the states go down by a factor of 10, and so it's just, okay? And so this is what you're seeing, okay? You're seeing that N naught goes exponentially with this EF minus EC. If you, so at every, if you do the integral, right? I'm going to do the integral. I want to solve for N naught. I need to integrate from EC to infinity of f of E, which depends on EF, times GC of E, dE, is my final expression here going to be, is there going to be what's going to happen to the variable E after I do this integral? It's going to go away. It's a variable of integration. Okay, so it's gone. So even though I was talking about things with respect to E here, what I'm going to see is I'm going to get some expression. We get the integral of this. It's an exponential times the square root of E. Okay, that's what it's going to look like. I'm going to get some expression that's going to be an exponential. Integral of an exponential is an exponential. Okay? Now, I'm doing it very gently because I don't want to spend all my time with the math. But as I integrate this to infinity, that exponential is going to die out, and that's not going to contribute at all to my integral. You do this, and you'll see. You have the exact functions for these, you do your math, and you're going to see that this limit just evaluates to 0. Okay, so then this integral just depends on, you're going to see it's going to depend on the difference between EC and EF. Right? Because f of E had some form. Okay? E minus EF. You're going to evaluate this from EC to infinity. I'm just giving you an idea that, you're going to integrate an exponential. Okay? You're going to get that exponential back. Your final solution is going to be kind of an integral evaluation of this. Exponential of minus infinity is 0. And then you're just going to get an exponential of minus EC minus EF. Or EF minus EC. Which makes sense, right? It's kind of the same thing. The same thing I said before holds true. It's just now referenced with respect to the Fermi level. If I screw my Fermi level down by 60 millivolts, I'm going to still see this exponential decay. Yeah, I'm going to see it decay by a factor of 10. Okay? And I've already done all this. I can use some, the only thing special here is to evaluate this and just doing some U substitution to evaluate the integral instead of having it as, this function as E minus EF. I use some variable, but this is what I get out, okay? So here's my integral when I've done my substitution, substituted for E, wrote it in terms of a different dummy unit of integration. And then now I'm integrating from 0 to infinity because I replaced the E. Okay, this is just how you do an integral. What you're going to see come out of it is there's a prefactor here. And that's going to be the same, no matter where EF is. This just comes out. Do the substitution, it doesn't matter where EF is, it doesn't matter where EC is. I just get this prefactor. I do my U substitution, I get this prefactor. And I can write this prefactor, I call it some effective density of states. I don't want to solve this integral every time I want to know my carrier concentration. I want an easier expression. Okay, so I get this expression. Oh, I'm sorry. Sorry. I should say one more thing. This integral here, they're doing the full Fermi-Dirac integral. Okay, so they can't solve it analytically, so they're leaving it in this form. Okay, so even in the Fermi-Dirac form, where that's the case where EF is not, E minus EF is not necessarily satisfying this. This is just the exact. Okay, you can write it in this form. And this thing, if you do the approximation, you still get the same prefactor outside. Okay, and that prefactor is what we call the effective density of states. That's the number of states per cubic centimeter. And this is the density of states is some number of states per cubic centimeter per electron volt, right? Per volt. This is really, there's no electron volt here. So it's kind of telling you your effective number of states in the total conduction band. Now it's not really telling you the number of all the states, it's kind of occupancy weighting them. Because the only states that really matter are the ones near the band. Okay, so but we're going to see how we use it in a second. So for all you care, the effective density of states of the conduction band is a number. Look, it depends on the effective mass, look, it depends on KT, but at room temperature, it's this number. It's 3 times 10 to the 19 per cubic centimeter, okay? Now this is doing it all with the Fermi-Dirac statistics, and this has a name. It's called the Fermi-Dirac integral of order 1/2, right? You can feel special, a special math function. It doesn't have an analytical solution. It has approximations in certain limits. And one of the approximations of this is in the limit where this is true. And so, when this is true, you're going to see that what this evaluates to is just this exponential EF minus EC. Okay? This is the exponential decay. So this is plotting this is just plotting the exact integral. Okay? So here I have this Fermi-Dirac integral. I'm plotting that Fermi-Dirac integral as a function of EC minus EC minus EF. Here, EF is in the conduction band. Here, EF is below the conduction band. I'm just plotting what that exact integral looks like. And as long as EF is far enough below the conduction band, it's just this exponential decay. That's as if we had done Maxwell-Boltzmann and everything's the same. Now, as my EF gets closer, that integral starts to kind of look different, and it has different behavior. There's approximations to it in that regime as well. That's called the degenerate regime. So I can define the degenerate regime in several different ways. That's when Maxwell-Boltzmann no longer holds. It's also when I have a lot of carriers in my band. It's when the number of carriers in my band is approximately equal to my effective density of states in my band. It's also when, E minus EF is less than this. They're all equivalent ways of saying the same thing. The degenerate regime is when Maxwell-Boltzmann no longer holds. Okay? When Maxwell-Boltzmann holds, you get this nice exponential dependence of that integral. Okay? But really, we're going to focus in this regime, in the Maxwell-Boltzmann regime, because that's where we can get analytical expressions. Otherwise, we have to leave everything in this form. And if I were to ask you, well, what's the dependence, is this and that, it gets all convoluted. Okay? I think it's a lot clearer to just make the Maxwell-Boltzmann approximation at first and do the integral. And if you do that, you're going to get this. Okay, I've already given you some intuition as to how you get it, but you just put the stuff in and do the integral and you get this. And you can see that the exact integral goes to that in the limit where the Maxwell-Boltzmann holds, okay? But that's all this is all saying. Okay, so the number of electrons in the conduction band, and this is a very, very good approximation as long as Maxwell-Boltzmann holds. So don't let it fool you. This is like, under this condition, this approximation has like 1% error or something like that, or less. You can calculate what it is at 3 kT, but it's not. This is a very good approximation. Your unknown in kT is a lot worse than what this is, because you don't know the exact temperature. Remember, and this is exponential, and so if your temperature is off by 5 degrees, okay. So this is telling me the number of electrons in the conduction band is equal to this effective density of states, that's kind of weighted by some probability, times this exponential function. And this exponential function is related to, where's that coming from? What's giving me this exponential function?
Probability.
Yeah, my probability. It's just coming from my probability. Okay? Oh, it looks very similar. I could rewrite this as EF minus E. And interestingly, when I do that whole integral, if I weight this, it ends up becoming EF minus EC. That's the important energy. Why? Because that's where I first have states, and then it's all decaying after that, right? So this holds exactly the same as before. What you should take away is the same picture. I can never remember the minus sign. What I know is as EF gets closer to EC or above it, I should have more electrons, and then I figure out the sign here. Same thing with the valence band. The valence band is going to have the exact same expression. P naught is going to equal some NV, some effective density of states of the valence band, but it's going to depend on EF minus EV, but it's actually EV minus EF, okay? Why is that? Well, I know when EF is much larger than EV, my number of holes is decreasing exponentially, right? As my Fermi level approaches one of the bands, my Fermi level approaches the conduction band, I have exponentially more electrons. When my Fermi level approaches the valence band, I have exponentially more holes and exponentially fewer electrons. Okay, and so this is the degenerate regime where you do the full Maxwell-Boltzmann statistics. Okay, you just do the math, but it doesn't go as exponential because your Fermi function when you're looking at states in this region, if you do a shift, the states aren't decreasing exponentially with E. they're only decreasing exponentially with E in this table. If this is f of E is a function of E. Okay? How many holes are there? Holes get neglected in this course, okay? It's all the same thing, just gotta watch your minus signs, okay? So you get the same sort of intuition, everything works the same. Oh, you gotta do this 1 minus f of E, that's fine. We know that 1 minus f of E, I can write it as an exponential of E minus EF, right? Over KT. And here they're doing it exactly. Now look, for the valence band, my effective density of states in V for the valence band is very similar. And so this isn't going to give you much error in this course, okay? If you're trying to calculate the carrier concentration in this course, you're looking at something at the power of 10 to the 19. I don't care about 0.1. Okay, you can give me the 0.1, that's fine, but you know, let's not kid ourselves and think we have infinite accuracy, right? If I change my KT by just a little bit, it's going to change this integral to Y. I would change this expression to Y, because it's growing exponentially, right? So if I use 25 millivolts or 26 millivolts, I'm gonna get different answers, maybe by a factor of 2. But okay, like, all of these are approximations, and the whole point of doing this is to get intuition as to what's happening, right? We're just trying to model things, and all the models are assuming everything's perfect. You know, for us to really get the exact number, we're gonna have to model all these extra non-idealities, which generally, even if you're the best simulationist, you don't know all these non-idealities, like how many defects there are in the crystal, what's happening at the surface, this and that. Okay? So this is kind of the key point to take away. Okay? So here I'm moving EF. Okay, here are my band edges. Okay? And this is a log. Remember, my carrier concentrations are growing exponentially. So for me to show them on any scale that you can see anything, I have to show them on log scales. Okay? And so in this picture, I'm moving my EF between the bands, and I'm telling you how many electrons and holes I have. Okay, let me start here. As I move EF towards my conduction band, I'm exponentially increasing my number of electrons, and I'm exponentially decreasing my number of holes. The NP product is going to equal a constant. That's going to equal Ni squared. Okay, I gave you a physical interpretation of it last class. Now I'm giving you the equation form. You get the exact same thing. As my EF gets close to my conduction band, I stop having that exponential growth, and it starts to bend over. It actually, instead of going exponentially with EF, it's going something like EF minus E to the 3/2 power, which is very different than exponential E minus EF, okay? And so it starts to roll over. So in this part, in the degenerate regime, I have very high, I'm degenerate in electrons, and my NP product is no longer constant. My NP product to be constant, I had to be in kind of reasonable concentrations of both electrons and holes. Similar on the valence band side. Okay, and this is where I have to use my Fermi-Dirac statistics. This is where I have to use Fermi-Dirac statistics. I don't have to use it for both carriers. I'd only have to use Fermi-Dirac statistics for electrons. Why don't I have to use it for holes here? Because if I look at my function, you know, my electrons would be maybe in this regime, but my valence band is in the exponential decay of this tail over here. So Maxwell-Boltzmann still works for holes. Another way to say that is, this is f of E, and this is 1 minus f of E, and EC was right here, and EV was here. I'm definitely in the exponential decay of this curve for the valence band, but I'm not in the conduction band. Did I lose everybody there? Only half of you. That's okay. Okay? I can compute this product, and here I'm doing it with the full expression, this f of a half. It's a special function, it's just when I'm doing full Fermi-Dirac statistics. This product is constant in the gap, as long as you're about 3 kT away from the band edges. Okay, and I have expressions for N naught. I have an equation for P naught. My expression for N naught depends on EC minus EF, exponential of EC minus EF. My expression for P naught depends on exponential of EV minus EF. If I multiply them together, the EF dependencies are actually going to cancel in the exponential, and I'm going to get something that depends on EC minus EV. EC minus EV is what? That's the band gap. That's just to keep you guys up, I'm sorry. Okay, so it's going to depend something on the band gap. This factor out here is the, that's just the multiplication of my density of states. And what we see is we can get an expression for Ni. Ni is equal to N naught P naught, N naught times P naught, when I'm in the non-degenerate limit. I can take the square root of that, I can take the square root of this function, now I have an exact expression for Ni. Okay, before I had a proportionality for it, now I have an exact expression. Okay? For a given semiconductor, Ni is not going to change unless I change the temperature. But the band gap basically stays constant. It changes a little bit with temperature, but not by number. Okay? So we had already discussed this before. Ni, just to remind you, we've got a lot of variables in this class. Okay? We're going to even have more. We're going to have N, we're going to have N prime, we're going to have P, P prime. Trying to remember the other ones. We're going to have a lot. A delta N, okay? So try to keep them all straight, maybe make a list, but Ni is the intrinsic carrier concentration. That's if you didn't have any doping. You didn't have any doping in your semiconductor. You're at a finite temperature. How many electrons and holes do you have? And what we argued is at a finite temperature, there's going to be some number of electrons and holes, because you have some thermal energy that knocks some up. And that's what Ni is. Okay, it's the intrinsic carrier concentration if you didn't have any doping. And so as Ni goes, as temperature goes up, Ni goes up, exponentially up. As Eg goes up, Ni goes exponentially down. It's harder, you have fewer electron holes. Another way you can look at the product of N naught P naught, as the band gap gets higher at a given electron concentration, you're going to have fewer holes. And as my density of states goes up, maybe as my effective mass gets larger and I have more states, erase my picture, Ni is going to go up. But these are going up differently, right? This is going up linearly, this is going, or square root linear, right? If both of them are going up by the same, these are going up exponentially, okay? Or this is going up exponentially, this is decreasing exponentially. And this is a good number to know, okay? So Ni is to the 10th. So I want to point something out here really quickly. And that's, I can already calculate things a bunch of different ways. And it's not 10 different equations. It's just like basically the same relationships, just putting them all together in different ways. I have an expression for N naught as a function of the density of states in EC minus EF. An expression for P naught is a function of the density of states, the effective density of states, the valence band, and EV in EF. I know my N naught P naught product is constant when I'm in the Maxwell-Boltzmann regime. So if I know N naught, how would I know N naught? You tell me that doping is higher than Ni. right? Well, that's how many electrons I have. That's typically what we assume all of our doping is active. Okay, so if you know N naught, how do you calculate P naught? Well, there's several ways you could do it. You could start off with N naught. You know what the density of states is. It's just a parameter for the material. They're in the back of the textbook. It gives you common values for different semiconductors. You can calculate the Fermi level position. If you know where the Fermi level position is with respect to EC, you can calculate the Fermi level position with respect to EV. Then you can use your expression that depends on the density of states of the valence band in EV minus EF to calculate the number of holes in the semiconductor. Or I could use this one, and if I know N naught, I know Ni squared divided by P naught is equal to N naught. I know Ni squared is 10 to the 20. If I know N naught is 10 to the 17th, then I know P naught is 10 to the 3rd. Well, I don't know what my Fermi level position is, so then I can solve for my Fermi level position. So that's, don't let it confuse you. We're just taking the same equation and we're putting them together enough. That's, I can calculate, I can calculate N naught and P naught and take the square root of that to calculate Ni, but Ni is a given material parameter. So, here's another question. If I have an undoped semiconductor, an intrinsic semiconductor, where is the Fermi level position? What is your estimate? In the middle. Well, there's a small, yes, but there's a small correction to it because the number of states in the conduction band and the number of states in the valence band are not always equal. If they're equal, it will be right in the middle. If I have a lot more states in the conduction band, then my Fermi level has to be lower so that I have the same number of electrons and holes, because that's what intrinsic means. I didn't put any dopants in there, so the number of electrons and holes has to be the same, because I knock an electron up, I leave a hole behind. I can't have more than the other. So if I do my expressions and I calculate EI is just, it's defined. EI is my intrinsic Fermi level position. It's just saying, where does my Fermi level lie when my semiconductor is intrinsic? I can take my expressions, right? I have an expression for N naught. I can say, well, when N naught equals Ni, what is EC minus EF? Right? I solve for what that EF is, and that's my EI. Now, EI is not absolute. It's always in reference to the bands. So it's either in reference to the valence band or the conduction band. I generally don't have an absolute energy scale. So in this case, this is in reference, this is in reference to the energies of my conduction band and valence band. So, I could shift these both by a fixed amount. I can shift my energy scale around, and that's just going to put EF, it's going to shift EF by the same amount. There's no absolute energy. All the energy is relative. Okay? So in silicon, because the density of states are so similar, EI is 1 millielectron volt above mid gap. Okay, for our purposes, it's at mid gap. So it's just at EG divided by 2. Okay, so in an N-type extrinsic semiconductor, not a different equation. It looks like a different equation. It's my same equation for N naught. N naught equals density of states of the conduction band times some exponential of EF minus EC over KT. I'm just solving that for EC minus EF. Okay? So I know what N naught is. Oh, well, if I put in some doping, what is N naught equal to? It's just equal to my doping concentration. So this is N naught. But I'm just saying, this is under the assumption that N naught equals ND. If I put in some known amount of doping, and that's higher than Ni, then my electron concentration is going to be ND. Okay, not a different equation, just a manipulation of the equation we already have. Same thing here. Look, this is a natural log. I have to change my doping by a lot to change my Fermi level. How much do I have to change my doping by to move my Fermi level? 60 millivolts. Ten times. A 10x change in doping gives me a 60 millivolt change in my Fermi level with respect to the conduction band, or valence band. Okay. And if my doping is less than Ni, well then my carrier concentration is just equal to Ni. Or it's equal to Ni plus the doping, but Nd is going to be much smaller than Ni. That's what I'm assuming. This is a logarithmic scale. That's just basically equal to the intrinsic carrier concentration. Okay. We did it. So what we did is these are the fundamental equations. You know, we solved for what my electron concentration is as a function of EF minus EC. How did we do that? We did that integral. The probability of state is occupied times the density of states in the conduction band. We did that integral. We solved it using Maxwell-Boltzmann. You can also solve it using the Fermi-Dirac, the full expression. It gets more complicated, but then you take an approximation and you get this. That's just what you get from doing that integral. Do the same thing for holes, you get this. And then we're just taking all the other equations and manipulating them around to get all these things here. That's it. If we take these and we multiply them together, when are these valid? In the Maxwell-Boltzmann regime, we multiply them together. It's just going to depend on EG. I'm telling you this, EF drops out. You can imagine, multiply these together. The EFs cancel. I have a positive EF here, negative EF here, cancels. I just get a function that depends on the band gap. Okay, this is my intrinsic carrier concentration. N naught does not always equal Ni. Okay, if you don't know what you're doing in this class, it's going to be really hard because you're going to see this equation and say, oh, I know what Ni is, that's what N naught is. No, that's only when you have an intrinsic semiconductor. Okay, and somebody's going to give me that in the exam, and I'm going to be very, very sad. But if you have an intrinsic semiconductor, this is the case, and I can go and solve for all this stuff. But it's all these fundamental equations, okay? It's just written in very different ways, but it's all about, none of the physics is different, okay? And so we did it. Thank you for letting me do this makeup class. Really, you should be thanking me, but I don't expect that. And I hope this helps you with your homework. I think you should be really ready to go and knock out all these problems, and you shouldn't have to learn anything on your own. We'll have class on Monday. Homework is due Monday evening. You should be able to do it all now. We have a TA for this course. Ankur Napani, and his information will be posted on Courseworks. He will normally hold office hours on Fridays, but since homework is due on Monday, and since I'm such a nice professor, we're going to have office hours after class so that you can ask him any homework questions that you have. Okay? But typically they'll be on Friday, so that you've done the homework at home on Thursday night. You might have a few remaining problems, and then you can meet with him on Friday. I'm not exactly sure what time. I think he's telling me maybe 9 to 10, and he'll extend it after that if there's still questions. He's not going to cut it short. That's where you do all your learning. So, you know, I can talk about everything, and my job is not to do the math for you. My job is to give you the intuition. And then you have to play with the math and see how it all works out. But if you know where you're going with the math, it should all make sense, okay? So we will have office hours on Monday after class. Thank you guys, have a good weekend.